Hi. Boy, the last time I was at NANOG was probably about 5 years ago or so. No, wait, actually I was in Oakland. But this has gotten much bigger than I remember back in the early days when we met in the Bay Area, and it was probably about 1/3 or maybe 1/6 the size. Anyway, I wanted to talk about good engineering practices regarding wireless because I have seen a lot of people, a lot of ISPs decide to go out and get into the sort of the wireless business to try to circumvent the last mile that usually the corporate monopoly has a hold of, like various cable companies and telephone companies. But excuse me, my Mac decides to get a better hand on it here. Okay. And there seems to be a lot of network kloofulness, but there's not that much RF kloofulness that I'm seeing deployed. And because of that, they're deciding to use a lot of unlicensed spectrum where things tend to be somewhat more anarchistic than licensed spectrum. And because of that, there's a lot of people stepping on each other's toes. And I want to talk about good engineering practice to be able to ensure better uptime for your network as well as other people's networks to prevent interference and such. So next slide, I want to talk about good engineering practices, which is, there we go, oops. Nope. This is called Star Office on a Mac. Okay, standards of good engineering practice. That used to be a term that the FCC actually previous to the FCC, which is called the Federal Radio Commission, used and eventually morphed into the FCC's rules and regulations. I'm not sure why it's freaking out like this. Go back. To that, it's actually currently meant as kind of a set of standards or as the proper way of doing things to ensure more uptime and minimize interference to yourself and to other people. So a lot of people are using, as I mentioned, 802.11, and I want to sort of talk about the upsides and downsides of that, and then how this works with good engineering practice. Obviously, the biggest reason is it's non-licensed. The big thing about that is that it's significantly less regulatory, hassle that you have to be able to do to be able to get these boxes up. You don't have to no expensive licenses or coordination. The arcane regulatory knowledge needed to license radio is not needed. And when I mean expensive licensing and coordination, by the way, that can end up being like tens or maybe at least single thousands of dollars or tens of thousands of dollars sometimes for coordination and such, for license. The hardware cost is magnitudes less than the equivalent license technology. If you had a standard sort of carrier class radio, this is why we have Macs come up here beforehand to test them out. Okay. I need them. Even less, okay, so a carrier class radio may cost tens of thousands of dollars and so, whereas you can go out and get an access point for $50 or so. It doesn't necessarily mean it's appropriate deployment for outdoors. Obviously, getting 11 to 54 megabits, well, in reality, it's actually something about half of that, is a big win over those old wireless radios that only did 19.2. This is going to be frustrating, I can tell after about 45 minutes. I don't know what it's doing. It's in the Darwin X mode, because I have to use Star Office. Obviously, 802.11 is a little bit more plug and play because it's based on Ethernet standards, and actually the software, pretty much any modern operating system can support it. Why not use 802.11? Well, and this is where we're going to start getting into it. The biggest reason is it's non-licensed. Non-existent coordination facilities. There are a couple of companies or organizations that are trying to put coordination back together. One of them is a company called, or an organization called Bank, which is in the Bay Area. And there's going to be a number of more, there's going to be more ad hoc coordination companies that are going to try to do this in the future. There's other users also on the bands that you have to be consider. I have a paper out there, if you go to www.lns.com/paper/part15, that goes into the about 12 other types of users that are on like 2.4 or 5.8 megahertz or gigahertz bands. Some of these people actually carry guns, and they get really upset when you start interfering with them. They're called public safety, and they use it for things like video between helicopters and the ground and such. And if you interfere with them, they tend to take you to court pretty quickly. There's other issues besides that. Well, the biggest thing for unlicensed is that you have no priorities over any other traffic. If you go into the FCC rules and regulations in Part 15.5, it says operations of an unintentional or intentional or unintentional or incidental radiator subject to the conditions that no harmful interference, and I'm not going to have, wish I knew this by heart, is caused, and that interference must be accepted and may be caused by, I can copy this off on a USB and give it to you that way. Basically, you have no rights. Oh, can we just use yours? Yeah. Okay. Exact same box.
It's coming.
Do you have it in mirrored mode? No. Take up most of my time just playing with Macintoshes. Okay. So anyway, you have no rights over any other users of the band, and particularly you don't have any rights over licensed users that are out there. And again, licensed users vary from television stations to people like public safety and such. Also, why not to use 802.11 in particular? The protocols have problems scaling. A lot of people are trying to solve that. A company called Etherlinks and Cisco's have solutions by doing things like changing the ACK window time so that you can actually take these things for longer distances than what they were originally designed for, which was just minimal hundreds of feet. Modifications to the standards will help minimize interference. Also, automatic power control and frequency selection, which is one is called 802.11h, which is mandated by the European Union, but is not here, unfortunately. Outdoor deployment requires some RF engineering knowledge. In fact, I prefer a lot to minimize interference issues and other regulatory issues one has to deal with, such as radio frequency radiation exposure standards. And there's a lot of people out there with tin hats that tend to get a little scared about this stuff too. So you'll have to deal with usually people complaining about you deploying these things. And of course, there's various local ordinances on antenna deployment and such. Building an expensive network on 802.11 or unlicensed can be as risky as you have no rights or priorities, and you may sink a lot of money into this thing. So we suggest that you coordinate with other licensed users and unlicensed users. A properly designed network will survive longer, and other issues can affect you, like FCC rules changes or pressures to get the FCC to enforce rules. Be active in watching and challenging and hopefully changing the FCC's rules. So let's get a little bit more. That's sort of the why we're doing this. I want to talk a little bit about good engineering practices for RF deployment. Basically, from point A to point B is what you're trying to do. You're trying to get a radio signal from one point to another. And proper radio engineering, using good engineering practices, will only put enough radio frequency energy to get to the reception point. It's not going to go anywhere else. And hopefully, if I want to talk to that person way over there, I'm just going to send the RF energy over to there and sufficient enough power so he or she can receive it. I'm not going to send it out over there because that'll start interfering with that person over there who may be trying to talk to somebody else. So there's kind of like two vectors you have to work with in designing an RF link. One is the power to get it to the location, and also the amount of turf that you're covering. Again, I don't want to cover that turf because somebody else is using it, but I just want to cover this turf over here. So the basic sort of link design that I'm going to do to be able to get from this podium to over in the corner over there has to be done for pretty much for every deployment. Depending on the complexity of the deployment, the engineering study requirements will change. It gets down to, can you get to the signal from one antenna to the other so it can be successfully used? So we're going to talk about engineering the link. Antenna requirements. This defines gain as well as sort of shaping the beam to be able to get from one point to another. For instance, if I'm going to be doing point-to-point, I want a very narrow beam. If I'm going to be doing point to multipoint, I may want a very broad beam. We're going to talk about that a little bit later too. Signal requirements, transmitter power and signal strength needed for the receiver. So how much signal does the receiver need to be able to actually decode that RF? In a site survey, you're going to be doing, for short distances, you can pretty much sort of look and see if it's going to make it. So I can tell that I can probably get to that exit sign in the corner over there. But if I was doing something a little bit farther, maybe more than a couple hundred feet, I may have to actually do some computer modeling to be able to figure that out. There's a bunch of software out there. I'm just going to touch on some of the expensive ones, and we're going to actually show details on a free one here. EDX makes a really nice software package and software modeling package, but unfortunately it costs like tens of thousands of dollars. If you're doing a lot of work, like if you're a cellular telephone company or something like that, EDX would be a good solution. Something a little bit cheaper, a company by the name of PathLoss puts out for about $4,000. If you're doing sort of like, if you're a standard sort of an ISP and you want to make sure that you can get your backbones working and such, I would probably invest in this. If you want something really cheap, it's actually free. There's a company, there's a package out there called Radio Mobile, which actually kind of is, actually in some ways it's more accurate than the others because it actually uses the shuttle RF elevation modeling that they did about 3 or 4 years ago. And so it's actually accurate to about 1 meter for elevation and terrain and such. But the more you pay, the more accurate uptime and coverage predictions you can get. What they do is the more expensive ones have better knobs for tuning adjustments like weather and things like that. And they actually have a little bit better modeling because they've been doing it a little bit longer, and actually it reflects reality a little bit better. You also have to understand real and potential interference. Look around. What antennas do you see nearby? If you're going up on a mountaintop, you may want to look for things like ENG antennas or electronic news gathering. They tend to use the same frequencies you will be using at 2.4 gigahertz. They will tend to interfere with you very nicely. In fact, we're already starting to hear reports. Pac-Bell Park decided to put a very large 802.11 deployment in Pac-Bell Park, and they hadn't really thought of the ENG trucks that are going to be going in there covering the news or the sports events, and it's starting to wipe out the users of the 802.11 network. Oops. But they didn't think about that. So you may have to think about that when you especially go up to a congested mountaintop. Look at also objects that nearby that will cause multipath, and we're going to talk a little bit about that later. But those would be things like buildings, a plane of water, a body of water that's possibly next to you, things like that. You could do some non-intrusive testing by just sort of sniffing around. So the cheap and dirty way is using things like NetStumbler, DStumbler, or something like that, and be able to see what other Wi-Fi or 802.11 deployments are out there. But again, there's about a dozen other users of this band, and that's not going to look at those other users. So you're going to have to probably haul out not a cheap spectrum analyzer and a Yagi and be able to sort of sniff around and see who else is out there. So a spectrum analyzer will be able to see non-802.11 RF. Worst case, you can always sort of try it out. Bring a mask and a 24 dBi dishes, the standard sort of $70 24 dBi dishes, and see what happens. And look at signal and noise levels and see if it's going to be usable. So when you start working with the engineering software to do this, the questions you're going to be asking that software: can the antennas see each other? and we're going to go into this a little bit later. Do objects cut into the Fresnel zones? And again, we'll talk about that in the later slides. What's the free space path loss? What's the predicted uptime of the path determined by the frequency, effective radiated power, distance, weather, type of terrain, and such? So I'm going to go into link budget and path loss for that. You have actually two things that you have to figure out. It's just a simple mathematic formula to figure out if you're going to have enough signal from point A to point B. You're going to have a lot of gain in certain things like antennas. You'll have gain in the transmitter and receiver amplifiers, and maybe and you also have gain effectively in the transmitter output. You're going to have loss in things like coax, connectors, what's actually called free space loss, which is the loss between one antenna and the other antenna, which ends up being at least 96 dB, and then whatever mileage that you're going to have between those two. You're going to also have obstructions that will cause diffraction, which will actually cause attenuation as well. And then atmospherics. In other words, how much rain do you have, how much snow? At 2.4, it doesn't really become a factor, but if you're starting to use like the 60 gigahertz band, you're going to have a problem. This is a simplified sort of schematic of what gain and loss you're going to have. For instance, at the transmitter you have there, you're going to have a certain amount of gain. You're going to have free space loss between those two antennas. Again, you have gain in the antenna, loss in the transmission line, gain in the receive antenna, loss in this transmission line, and then some receiver sensitivity that you can have. This is a sort of a plot of signal level through the path. You'll have lots of signal at the transmitter output. You'll have a little bit of loss on the coax, a lot of gain in the antenna, a lot of loss in the path, and some gain in the receive antenna, and then a little bit of loss in the coax. But hopefully the receiver can receive this amount of signal that you're giving it. I have a simple path calculation you can actually get at my website called lns.com/pathcal. And it's just an Excel spreadsheet, and there's also a Perl script up there that actually will figure it out for you. And it'll actually just sort of, you stick in how many watts you have, what frequency you're going to be running at, antenna gains, things like that. It'll actually tell you what's called the fade margin, which is the end result, what you need to know. Fade margin is the amount of signal over what the receiver needs to be able to receive the signal. And typically for longer links, you want a higher fade margin because you know that you're going to have more variety or more varied signal between high and low of what you're going to have. Like through atmospherics and such, it may actually attenuate a little bit more during the day or night or whenever the rainstorms come through. Other issues that you're going to have to deal with are things like, again, atmospheric attenuation like rain and snow. Refraction. Refraction it can be best explained as if you take a glass of water and you stick a pencil in it, you'll notice that if you look at the pencil from the side, the pencil sort of bends. Well, in the case of, you can have the same sort of effect through the atmosphere, especially with longer paths like maybe 10, 20 kilometers or something like that, where the atmosphere actually will bend the signal. And with that, a lot of people will actually try to put diversity antennas. In other words, they'll put like one or two antennas, or two or three antennas, up a tower to try to compensate for that. The refraction will actually bend the signal up and down as it gets to the receive end. So if you have a very tight beamwidth antenna, you may have to put multiple antennas there to be able to cover it. Marine layers will actually do this as well. If you have a hot and cold sort of layer that'll come in, it will actually bend the signal as well. And we're also going to talk about Fresnel zones. Fresnel zone is a circle or a zone that will go around the center beam width that you need to clear in order to be able to get your signal from, again, point A to point B without significant attenuation. Typically, you'll need, there's a calculation I'll show you a little bit later, but you need to clear at least 60% of what's called the first Fresnel zone, and hopefully all of the first Fresnel zone, but 60% is a good rule of thumb. You can tell at this schematic that a Fresnel zone sort of widens out in the middle and then gets skinny on the ends here. So for instance, if you have a building that is, say, in the middle of here that cuts into this Fresnel zone, then you can expect a significant amount of attenuation at the receive end. That same spreadsheet that I told you about also will do Fresnel zone calculations. And all you have to do is put in the miles, how far out the obstruction that you have, and you can figure out how far or how wide the Fresnel zone is at that distance. So in this case, I said that we have a path that's 5 miles long. About halfway through the path, about 2.5 miles, we want to know how wide the Fresnel zone is. And the first Fresnel zone is about 50 feet at that point. So you need to be at least that much clearance in the middle of it. Here's an example of why it's a factor, and this is a path that I did for an Indian reservation up in North Dakota, where we were trying to get from point A to point B. The receive antennas and the transmit antennas are actually on towers. That's why they look they're above that ground. We can actually see the two locations, that red line, but you'll notice that the blue line, which is the Fresnel zone, is being cut into by a mountain that's halfway through. So this is actually not a good candidate. What we'd have to do is actually raise one antenna or both antennas to be able to clear that Fresnel zone. Also want to talk about multipath. Multipath is typically done, you encounter that, in fact you'll hear this like on FM radio when you're going through like downtown or something like that, you'll hear this whop, 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 whop sound. And what that is two signals arriving at your receiver at different times. Typically you'll have a direct path which will come from the transmitter to your receiver, and then you'll have some radio frequency that may bounce off of a building and then get to your receive location. But because it has to bounce off to some other building and get to you, it's going to take a longer path to get to you, and therefore it's going to be slightly out of phase. In fact, it could be 180 degrees out of phase and therefore cancel out the other signal. So typically this is something you have to consider if you have buildings next to you and you have to be concerned about multipath, whereas a signal may bounce off that building and interfere with your direct line receive signal. The way to get around that is to typically have a very narrow beam width antenna to hopefully ignore or attenuate signals that may be coming off axis. You can also address it by using antennas with different polarizations, and we're going to talk about antennas in a second too. Other interference issues, are there other users on the band? You may want to coordinate with those people, or you can change frequencies, or you can do a number of other things. So we're going to talk about point to multipoint a little bit. I'm going to show you the radio mobile mapping software a little bit, at least one of the outputs of it, and show you what it looks like. Questions, again, you have to ask yourself, how many clients can you see your access point? Where are they located? What sort of signal strength can the clients expect? Typically, the way that you do this is through kind of an elaborate form of what would be known as ray tracing. There's a couple of different propagation models on this. One's called Longley-Rice, the other one's called TIREM. And you can find, again, radio mobile or EDX or various other things. Software prediction models will usually use these. Both will actually over-predict to some degree about 5 to 17 dB or so. So actually, they'll actually give you a little bit better than what you're actually going to get out there. And you have to use sort of that and a little bit of experience to be able to understand the modeling. The more expensive software, again, modifies these methods so they're actually a little bit more accurate. Again, this is a topology for point to multipoint. You do get into things like hidden transmitter problems, which I'm not going to go into details here, but this is, again, typical topology for that. This is an example of an output of the radio mobile program. This is actually my transmitter, my access point that's out in the sunset of San Francisco. To the left, you see the Pacific Ocean. To the right, that's actually San Francisco. You can see that it's the red is actually the largest signal strength. The purple or whatever is actually no signal strength. You can tell that there's some mountains or kind of hills to the right there. Just to give you some scaling, you can overlay, I think it's Yahoo Maps or MapBlast images on this thing to be able to sort of get an idea of what scaling and such. So you can see Golden Gate Park up there and such now. And this gives you a good idea of what sort of signal strength you're going to see at for your clients around there. Different antennas for the different kinds of jobs you're going to have. Point to multipoint, in that case, you're usually going to have an omnidirectional or some sort of sector antenna at the center point. Omnidirectionals are usually discouraged because of spectrum pollution. Again, we were talking about polluting the spectrum over here that I don't want to, I don't have any clients that need to listen to me. You just want to aim an antenna over to the other direction where your clients are. So in the case of point-to-point, you may use a directional on both ends. Point to multipoint, for instance, your typical little laptop card uses what's called a dipole, and that is actually a PC that's usually etched on the edge of the PCMCA card. Has very low gain, radiates in almost all directions equally well or equally badly, depending on your point of view. It's an omnidirectional antenna will usually have gain to some degree, and what they do by that is, and a little bit of antenna theory, is how you have gain is you actually take energy that you would normally be going in all direction and you kind of squeeze it down and focus it out someplace else. So think of a flashlight. When you have a flashlight, when you have it unfocused and the beam is really spread, it's kind of a dim beam, but as you focus the beam, where it actually becomes more and more narrow, it becomes brighter and brighter. You've actually increased the gain in that direction. So an omnidirectional can have gain by taking the energy that would be going straight up and straight down and squeezing out towards the horizon. Other antennas you'll be looking at as panels or sectors, where what will happen is those are good antennas for putting up on a mountaintop if you need to cut up a pie-shaped coverage area that you need. You may only want 90 degrees, but you don't want to be sending it way up here and way down here. You have a population area that you're trying to cover. So you may only have a beam width around 15 degrees this way, but you may want to cover about 90 degrees this way. So that's typically what you see as a panel or a sector. Here's some polar plots for an omnidirectional antenna. This is one that was actually used at Burning Man a couple years ago, covering that area. So you can see on the bottom, it's pretty much a circular pattern, but if you look on the top, which is the edge on, you can see some horizontal gain where it's not producing any energy up or down, but it's pushing it out towards the horizon there. This is a panel or a sector antenna. You'll see a lot of gain. Again, this is edge on the top, or that's kind of like if you're looking at it horizontally. There's kind of a tight beam width, maybe about 15 degrees out towards the horizon. But if you look from the top down, it may have a beam width around 30, 40, 50 degrees there. Directional antennas do not radiate in all directions, again. This is hence the name directional antennas. The more focusy antennas, the higher the gain, which we talked about, and will either have vertical, horizontal, or circular polarization. Why use a directional antenna? Helps your system be a good neighbor, raise the effective power of the distance point you're trying to serve, reduce interference to the path, reduce interference to others, which we sort of covered. Quickly, a couple other antennas, a Yagi, which is actually kind of small, or actually usually a little bit more compact and usually more aesthetically pleasing. Will have about 15 to 18 dB of gain. You can make them vertical or horizontal polarized. There's a parabolic antenna, which is the typical sort of $70 antennas that you can get, 24 dBi gain. There's also helical antennas that you can get. Now, this is a hand-made one that was done over PVC pipe. It has circular polarization as opposed to most antennas, which are vertical or horizontal polarization. Now, I should sort of touch a little bit about why you use polarization. Polarization is a good way of sort of attenuating multipath, or actually trying to squeeze more radio signals into a particular band. So for instance, in the latter, for satellite reception and such, you may have a satellite way out there, but you're going to use one particular polarization to pick up one signal, and you may use another particular polarization to pick up another signal that may be on the same frequency, located in the same direction. It works something like that for multipath. For instance, if I have a body of water out there that I'm going to be shooting across, I may get some multipath that's going to bounce off that body of water. In the case of what happens is it bounces off the body of water, it's going to be horizontally polarized. If it was going off a building, it'll be vertically polarized. If I use an antenna that's 90 degrees to that, I'm going to be attenuating the signal that's going to be bouncing off the water or bouncing off the building. So it's a good way of sort of minimizing multipath. Nice thing about helical antennas that are circular polarized is that you don't have to care about if it's a horizontal body of water or vertical building. What'll happen is the left-handed or right-handed polarization that you have for the circular antenna will reverse no matter what. If it's a horizontal or vertical body of water, it'll be the opposite and therefore be attenuated on the other end. Usually find a lot of ENG trucks will use helical antennas because they can't predict what sort of multipath that they're going to run into. So polarity is a product of the design of the antenna. Each end of the link must match or you're going to be attenuating. Can be used to minimize multipath and interference, which you talked about, and I sort of went over various horizontal and vertical and circular advantages and disadvantages. The biggest thing that you're going to have when you're deploying your system is interference, and it's going to usually be interference from others, and I've sort of mentioned that in the past. The bands are crowded, and the channels overlap, at least at 2.4 gigahertz. The only frequencies that we can really use is 1, 6, and 11. And it actually was sort of annoying when I fired up my my laptop and I noticed that there was a bunch of access points on channel 4 that the hotel was running. So that means that it wipes out channel 1 and channel 6 for being usable. So typically you really only want to light up on 1, 6, and 11 to be sort of a good neighbor. You need to coordinate internally with yourself, obviously not to step on each other, and you also need to coordinate with the other band's users. We talked about that. Here's an example of the 2.4 band plan that they have. Again, the ones in blue here are the ones that you can actually use, and the other ones overlap. You can see that each channel overlaps here. If you're coordinating with yourself, obviously you want to make sure that your access points don't overlap in channels and frequencies. I'm not going to do that one. This is an example of a box that we're deploying at Barn. I just want to sort of mention it really quickly. It's because there was some interest by a couple of people here where we find that most access points out there just don't have the security or the software that we need to be able to do to be able to deploy the stuff out there. Like for instance, we want to do QoS. You usually won't find any access points or very few access points that will be able to do that. So we're actually rolling our own. Another example, I'm going to skip past this. You can look at it on the slides or you can look at the Barn site. Other hardware considerations, a lot of people are deciding to use amplifiers to sort of power through their problems. This is a good idea and a bad idea. Usually it's a good idea if you can't explain it for any other reason from getting point A to point B. It's a bad idea if it's just a problem where you just need to raise your antenna up a little bit. Also, a lot of amplifiers out there are pretty noisy and they tend to pollute outside the channel that you're actually using it on. So you may want to try to avoid that if you can. There's also some regulatory issues, hopefully that'll soon be deregulated, where you can't necessarily just sort of buy these things and mix and match them between antennas and transmitters and such. Keep in mind, if you're going to be putting out, get the proper cable to put this stuff out when you deploy this. Use something like LMR 600 or LDF 450 or something like that, a really nice fat low loss cable, and you're not having to overcome that with amplifiers. Other issues that you may consider things like battery backup, how hardened do you want the site to be, grounding and lightning arresters. I'm going to show a slide, talk a little bit about grounding here. That's going to be a big issue, particularly if you're on the East Coast where you have a lot of lightning, whereas we're on the West Coast and we don't have a lot of lightning. No 100% way to protect it from large direct lightning hits. You can minimize the damage with static buildup and small discharges through proper grounding and various types of dissipation devices, which one is called Static Cat, which actually looks like this big sort of Brillo pad that you may put on top of your tower. Static and lightning will tend to build up on the highest devices like antennas and towers and such. Whatever you can do to be able to dissipate that, not as a point but as a multipoint. Discharges will go through the most direct route to and from your ground. In other words, power doesn't just come from the sky, it actually comes out of the ground too, up to the sky. Don't design installations where your equipment is the best path. You want to be able to have some other path to be able to have that lightning discharge. So you want to make sure the tower or pole is grounded, transmission line is grounded, and also provide a proper ground and a common point, which means usually large copper stakes in the ground with very nice fat copper wire going to a common point that you can distribute with. There's also grounding and lightning arresters. I'll just touch on this real quick. This one's actually kind of nice because this is what's called a gas discharge, and you can see in the there's a little circle right about here, and that actually is a little gas discharge pellet or whatever that goes into this hole here, and it prevents. What it does is it's kind of like a neon bulb. After a certain voltage, it actually conducts at a very low resistance. So if you have a lightning strike on the center conductor, it will actually go to ground very nicely. So it doesn't really conduct until a strike happens. Additional weatherproofing you'll need to worry about. Sealed transmission line connectors, really well. That's a big problem. I see a lot of people use just standard PVC or electrical tape and wrap stuff up, and then about a week later you see it flapping in the breeze and such. Use outdoor cable, coax and Ethernet. Ethernet, Belden makes a really nice Ethernet cable which has this stuff called Icky Pick, which is this silicon mess that they put inside the cable, and it's nice UV proof. Really hell to terminate, but it's very nice because it will last forever. Provide drip loops. Drip loops are typically a piece of coax or transmission line that'll just sort of go to like a drip or a little loop before it goes into an entrance, so that the rain will collect there and drop as opposed to getting drawn into the equipment that you have. Use light colors on the equipment to keep the internal heat down. In other words, paint the stuff white if you can get away with it. In the future, what we need to do is figure out how we can increase the bandwidth while still addressing the physics. In other words, the turf that we need to cover and the spectrum that we can use. Again, since a lot of these people are just putting this out there and just hoping that it works, there really isn't that much coordination. So we may have to consider some sort of automatic coordination for frequency and power. 802.11h, which again is demanded by the EU to be deployed over there, which is not a standard over here, unfortunately, which I'd like to see. There's things like mesh, which means that you deploy a bunch of little transmitters and such, maybe every block, so you don't have like one high power transmitter trying to cover a whole area, which may be a waste. Phased array antennas, there's a company called Vivado, which made with some success a phased array antenna, which means it's just one antenna and it electrically steers the signal. So if I need to talk to that person and that person, it will send out two different signals, but it doesn't have to actually reconfigure the mechanics of the antenna. It actually changes it through electronically phased. And then we're going to also see, and there's there's a couple NOIs and NPRMs that the FCC is looking at right now regarding cognitive radios that you may want to also track. That's so in the infancy at this point, but hopefully soon. Resources you may want to look at. Best one that I've seen out there is Rob Flickinger's book by O'Reilly. This is kind of a really good building community wireless networks or ISPs 101. Another one, Matthew Gast kind of has one, which is kind of a really tome. It's about this thick, and it's a good roach killer. The sort of meta network for a lot of these questions that you want to look at is freenetworks.org. That's kind of the meta site for a lot of the community groups and such. And of course, you want to look at the IEEE site for a lot of these standards and such. That's sort of it in a really quick nutshell. And I know that it was sort of long and sort of drawn out and dry, but hopefully at least touched on a lot of the areas that you'll be running into. If you have further questions, please give me a screen. Thanks. Hey, Bill.
Hi. Is the mic on?
Yeah.
Yeah, okay. One of the things he said right at the very beginning was that one of the easiest ways around a lot of these problems was to use licensed spectrum.
To use what? I'm sorry.
To use licensed spectrum rather than unlicensed. Can you talk a little bit about using frequency shifting to get commonly available equipment into licensed spectrum, or if you start out in unlicensed and then get a license, is this commonly done or not commonly done?
There's some spectrum that's going to be opening up for public safety that they're actually looking at trying to leverage off the commoditization of 802.11 and such, and the equipment out there to move it down into like the 1.8 and 1.9 gigahertz band and such. You could take the equipment that you have at 2.4 and try to license it at 2.4 as well. You can do this as a Part 101 user, and then be able to operate at a higher power. There's a lot of people there's a whole amateur radio community that is taking 802.11 devices, and since they get 100 watts as opposed to us, which we only get 1 watt TPO, they're starting to use this same equipment. But unfortunately, they're kind of restricted by the amount of what kind of content they can put over these networks. Does that sort of answer?
I was meaning to ask about frequency shifting devices, like the kinds of amplifiers that will also shift from like 2.4 up to 3.5 or whatever.
Right. Oh yeah, that's a good point. We're starting to see more equipment out of 3.5. Tsunami, Proxima is starting to make some stuff out there. You can use transverters and such to be able to move that up, to move common equipment like a 2.4 to up to 3.5 or 5.8 down to 3.5 if you want to as well. I haven't played with it that much. I don't know what the legalities of that is, so I'd have to look at that further. Yeah.
Charlie Khanna from NextWeb. I'd like to say, first of all, it's a great presentation. Secondly, I think one of the key points to really note here is the frequency coordination. As you pointed out, BANC is really important, and for those of you who don't know what BANC is, it is the Broadband Access Network Coordination Group in California. And we have a mailing list that you can join up for at www.wbank.com. And you can all sign up and you can see what other wireless ISPs are doing and get frequency information for the various sites that we have deployed there. So, thanks.
Yeah, thanks. I'm glad to see BANC out there at least. The only problem with these sort of frequency coordinations is, and maybe you can address this to some degree, is how do you, at least with license users, you take away the license if somebody does something bad. With unlicensed, you have to sort of like use peer pressure. So it's going to be interesting to see how this is going to, how unlicensed frequency coordination groups are going to work out. So anyway, just a quick takeaway. Try to use only the turf and spectrum you need. Coordinate with other users and tell them how to coordinate with you. And I also want to mention that there's at 12:15 there's going to be a wireless BOF that's going to be down in the foyer or whatever, right after the reception area, where we're going to try to compare notes if anybody has further interest on this. Thanks again, and we can wrap it up now.